What if I told you that every time you drive to work or to school, you're sitting on top of a machine that detonates a miniature bomb 2,000 times every single minute? And right now, if a car is driving past your house, the metal components inside its engine are changing directions 100 times every single second, experiencing forces thousands of times stronger than gravity and surviving temperatures hotter than molten lava. That isn't just a machine, and today we're going to be tearing down the internal combustion engine to see the exact mechanical engineering, thermodynamics, and chemistry that allow a block of aluminium to survive these extreme forces and move you down the road. So, every single modern gasoline car relies on a four-stroke cycle, also known as Otto cycle. To understand how we extract energy from fuel, we have to look at what happens inside a single cylinder during these four distinct steps. The first step is intake. The intake valve opens at the top of the cylinder. As the piston moves down, it acts like a syringe, creating a low-pressure vacuum that sucks a precise mixture of fresh air and atomized gasoline into the chamber. The second step is compression. The valve slams shut, sealing the chamber completely. The piston rockets back upward, crushing the air-fuel mixture into a space that's 10 times smaller than when it started. Now, the crucial engineering detail here is that compressing the gas doesn't just pack up the molecules closer together, it radically increases its temperature and kinetic energy. In thermodynamics, this is called the adiabatic compression, and it makes the upcoming chemical reaction vastly more effective. Now, the third stroke is called power. Just as the piston reaches the absolute top, the spark plug fires. The fuel doesn't just burn, it creates a rapid flame front that causes the gas to expand. This spike in pressure shoves the pistons back down. This is the only stroke out of the four that actually generates power to move the car. And the fourth and final step is exhaust. The exhaust valve opens, the piston travels up one last time, and it physically sweeps the spent hot gas out of the engine and towards the tailpipe. Now, here's where the mechanical engineering gets brilliant. The pistons only move in one linear path, straight up or straight down, but wheels need to rotate. So, how do we convert linear motion into rotational motion? And for that, we use a crankshaft. Think of it exactly like the pedals of a bicycle. Your legs move up and down, but because they push in an offset crank arm, the bicycle chain spins. But remember, the physics problem we just created, that only one out of these four-stroke produces power. If you only had a single cylinder, the engine would violently jerk during the power stroke and then completely stall out during the other three. To solve this mechanical instability, engineers do two things. The first thing they do is that they link multiple pistons to a single crankshaft, like an inline 4 or a V6 configuration, and offset their timings. This ensures that at any given millisecond, at least one cylinder is executing a power stroke to keep the crankshaft turning. And the second thing they do is that at the end of the crankshaft, engineers bolt a massive, heavy metal disc called the flywheel. Because of rotational inertia, the flywheel acts like a mechanical energy battery. It stores the kinetic energy generated during the explosive power stroke and uses that momentum to carry all of the pistons through a non-powered intake, compression, and exhaust strokes. This system is a masterpiece, but it faces a brutal limitation: the laws of thermodynamics, especially the second law of thermodynamics, which dictates that you can never convert heat energy into mechanical work with 100% efficiency. For you to have an idea, when you buy a gallon of gasoline, only about 35% of the chemical energy inside the fuel actually goes towards your wheels. the remaining 65% is completely wasted. So where does it go? It escapes as friction and extreme blistering heat. The steel and aluminum, all alloys used to build engines, have material limits. If the engine gets too hot, the pistons will literally expand too much, scrape against the cylinder walls, seize up, and melt the engine from the inside out. This means that engineers have to design complex cooling jackets and radiators just to pump gallons of liquid coolant through the engine block. Not to make the car any faster, but to simply throw away the excess heat energy so the metal doesn't self-destruct. For over 100 years, automotive engineering wasn't about reinventing the wheel. It was about optimizing this exact sequence of explosions. We added variable valve timing, double overhead camshafts, and computer-controlled fuel injections just to squeeze an extra 1 or 2% of efficiency out of this metal tube. Whenever we eventually transition fully to electric motors or find new ways to run these machines on synthetic fuels, the internal combustion engine remains one of the absolute peaks of mechanical optimization. So, thanks for watching, and if you want to have some more deep engineering breakdowns, make sure to hit the subscribe button and leave a like and let me know in the comments what video we should do next.